Hello everyone, this is Bharat here. Welcome to my peer graded assignment for the course Machine Learning Foundation for Product Managers. In this project, I'm going to follow the CRISP-DM framework, where I'll be going over the project work by following the 6 phases provided by the CRISP-DM framework, where I'll start with the business understanding phase, explaining the requirement here, then getting into the understanding of the data. Then let's see how we prepare the data so that it can be fit to the models. Then evaluating couple of modeling techniques, and then getting the research, and then finally the deployment. So let's start with the first phase of the CRISP-DM framework, which is business understanding. So in this business understanding phase, so we are given a project work where we will need to build a model to predict the electrical energy output for a power plant, which is combined cycle power plant. We have been provided with a data set which has 5 variables, as I shown in the table here. There are 4 input variables: temperature, ambient pressure, relative humidity, and exhaust vacuum. These 4 are going to be our input variables. And we have the fifth one, which is the target variable or the output variable, which is the energy output. So I have used some references here in this document. So I'm going to follow the Excel-based work here, where I'm going to use the capabilities of Excel to generate the modeling. I have also referred a couple of other areas. One obviously is the Coursera materials for this project work, and also I have referred some online materials for some of the work here. Getting into the data understanding phase, in this particular project, we have been given a data set which has around 9,568 observations for all the 5 input variables I spoke about. So if you look at it, it's a very good data set to start understanding our problem and evaluating the model. So let's prepare the data in our next phase. So getting into the data preparation phase. So I have split this data set of 9,500 plus observations into two sets. Number one, it is the training data where I have put 80% of the observations, which is 7,605 for 54 observations. And then around 1,900 plus observations I have kept for the test purpose. Now, if you look at the data that is provided to us, the quick observation shows that all variables here are continuous variables. If you look at the input variables, AP and RH, they are having a positive correlation with the output variable. Similarly, the input variables AT and V has also a positive correlation with the output variable PE. So considering these facts, our approach here is going to be use applying the multivariate linear regression, where we will be using calculating the predictions using the formula f of x equal sorry y equal to f of x plus b. So like I said earlier, we'll split the input data set into two sets: training set which has 80% of data and test set which has 20%. And for alternate approach, we are going to consider dropping one of the features, input features, based on the uh, correlation data that we'll be getting. We will drop the least absolute correlation variable, and we will redo the modeling with the remaining 4 variables. That's going to be our approach. So how are we going to proceed here? The first step is going to be the calculation of the coefficients. So like I said, I'm going to use the Excel's data analytics capability, where I'm going to use the regression capability of Excel to calculate the coefficients. In this in the first approach, I'm going to use all 4 input variables and build the model. The model will be trained with the training data set of 80%, and then we'll calculate the coefficients. In the second approach, we'll drop one of the input variable, which is going to have the least absolute correlation, and we will use the remaining 3 input features and build the model. For consistency, the model will be trained against the same training set that we'll be using in the first approach. Once we are done with this, we'll calculate the output metrics. So we will follow the we'll calculate output metrics like RMSE, MEAE, MAPE, and R square for both the approaches. And then we'll do a comparison and we will see which one best suits our project. So that's going to be the approach here. Uh, so just quick refresh here. So we have some formulas available for calculating the MEAE, mean square, MEAE, MSE, RMSE, and R square that we'll be using here. This is just a quick refresher. going to the fourth step, which is modeling. I'm going to start with the first approach. So using the data analytics capability of Excel, we have arrayed these numbers for the four input features. You can see at the bottom, we have the coefficient for each and every feature here. And similarly, using the same data analytics feature, we have removed one of the input variables from the approach one. Like if you see one of the input variable, which is RH, which has very less coefficient, it is removed in the approach two, and we have calculated the coefficients again in approach two. So we have the coefficients available for both the data sets for both the approach. And now let's evaluate the results here. Now here for the approach one in the evaluation phase, if you see uh, the section here in the blue, it is the input data for all the observations, and we have the output matrix calculated here. I have all the formulas updated. You can see in each and every cell the formula is updated, and we have calculated the coefficient output matrix. And if you see the final results at the top, we have a mean of 454, RMSE is 4.6, MEA is 3.65, MAP is 0.8, and R square is 0.92. So this is for the first approach where we have used all four input variables and we have arrived at these numbers. Similarly, I have repeated the same where we have ignored one of the input variable, the RH, and repeated the same flow for the remaining three input variables, and we have arrived at these numbers. And here, if you see the mean is 454.1, RMSE is 4.9, MA is 3.88, MAP is 0.85, and then R square is 0.91. So we have evaluated both the approaches here, and let's see the conclusion. What are our observations here? So if you look at the results from both these observations, there is not much difference when it comes to RMSE, like it is almost the same. The approach one gives 4.66 and approach two is 4.93. There is a slight increase in the MAE compared to both the approaches. Approach one has 3.65 while approach two has 3.88. Same goes with MAP. 0.8 is the MAP for approach one, and while 0.85 is the MAP for approach two. And finally, R square. If you see, approach one has a slightly higher R square, which is 0.92, when compared to the R square of approach two, which is 0.91. Now, what is the ideal expectation here? Uh, with these output metrics, the expectation is the RMSE, ME, and MAP should be as low as possible, while the R square variable it should be as high as possible. So looking at these expectations, the approach one, where we have a slight increase in the R square when compared to approach two, seems to be the best fit for our project here. So the conclusion here is we will follow the approach one where it takes the multivariate linear regression model with all four input features, and it is the better model to predict the electric energy output of the combined cycle power plant we are talking about here. Thank you very much.